In this unit, we're going to be looking at rates of reactions and chemical equilibrium. First of all, rates of reactions. So the pictures at the bottom, we see that chemical reactions can take place with fractions of a second or over millions or even billions of years. So there's really a wide variety of rates of reaction. Notice that there's a time element involved. So it can be measured in seconds or it can be measured in minutes or years. All of these time units help us to express rates of reactions. The second concept here is chemical equilibrium. So I have my ants right there at the top. They are stealing food from the neighbor's pile. And they transferred their little food nugget from one side to the next. To our eyes, the pile never changes. And this is the same as a chemical equilibrium reaction. The reaction can go both ways, and we know that we're at chemical equilibrium because we have the rate of reactants forming products equaling the rate of products forming reactants. Let's look at a general reversible reaction, and I'm just going to call it A plus B yields C plus 2D plus heat. So this is an exothermic reaction. And we're going to start off with just A's and B's. So these are all gases. And I'm just going to add A's randomly here and also some B's. So this is at the start of my reaction. And I'm going to flood my chamber with both A's and B's. Let's go ahead and count how many A's and B's we have at the start. I know I'm starting out with 0 products, so I'm going to fill that in. And let's count out our A's. So there's 7 A's and 9 B's. So in order for A's and the B's, or my reactants, to react, they have to collide with enough energy that they can hit hard enough that the bonds can break and reform into the products. And they also need to hit with the correct orientation. So just the act of just hitting hard enough is not enough. It has to be the correct orientation, especially if you have a molecule that is different on different sides. Let's go ahead and assume that our A and our B in this top left-hand corner react. So I'm just going to erase it, and it makes a C and 2 D's. So I'm just going to randomly pick an A and a B, and I'm going to write a C and 2 D's. Now, in the real world, these would be constantly moving, but I just can't draw that. The concept I want you to get here is that our reactants are forming products. Now, in a reversible reaction, eventually there gets to be enough products that the reverse reaction can occur. And how we represent that in our equation is by writing an arrow that's going backwards. So if you'll look right here on this equation, you can see that the forward reaction can occur and also the reverse reaction can occur. So reactants can form products at the same time that products can form reactants. So let's do a little bit of that, the reverse reaction. So I have a C and 2 D's collide, and they will form an A and a B. And at the same time, we have an A and a B colliding, forming a C and 2 D's. So this will occur until I reach what's called equilibrium. And equilibrium is when the rate of the forward reaction equals the rate of the reverse reaction. So let's say I'm at chemical equilibrium right now. Let's go ahead and count up how many A's, B's, C's, and D's we have. So how many A's we have is 3. By the way, these little brackets mean molarity, or moles per liter. So it's just kind of a quick way to represent concentration. So it's a 3 with a large M standing for molarity after it for the concentration for A's. Anytime you're given a molecular view where you have some dots you need to count that are representing molecules, just count them up, and the number that they have, that will equal the molarity. How many B's I have is 5, and how many C's I have are 4, and how many D's? 8. So if I counted that correctly, we are at chemical equilibrium. So let's go ahead and have products forming reactants and reactants forming products both ways. So let's say this A and B collide, and I get a C and a D. And then I have a C and a D collide, and I get an A and a B. So you're going to see that because the rate of reaction is the same with reactants forming products at the same rate as products forming reactants, at equilibrium, my concentrations don't change. So even though I am constantly forming products and I'm constantly doing the reverse reaction forming reactants, it will stay at equilibrium and my concentration will stay. This is what is known as dynamic equilibrium, meaning that the reaction is continually going. So it's never stopping, just like those ants on that first page. The reaction is going both ways always. So it's called dynamic equilibrium. Here is a graphic representation, and this is a very simple chemical reaction. So we just have two molecules involved, one reactant, one product. So if they collide with the correct orientation, then they can form the product. And if the product collides correctly, it will form the reactant. So looking at this chart here, I see that I start out with N2O4. So I start out with my reactant, and I have no product. So as time goes by with the reaction, the N2O4 is going to collide with itself and with the sides, and it will decompose and form the NO2. And you see that our NO2 amount increases. At this point, that is just a coincidence that we have the same amount. What is important is to see that when the concentration stops changing, I call this equilibrium. So when the concentration stops changing, it is called equilibrium. And notice that even though reactants are forming products and products are forming reactants, our concentration is going to stay the same. Here's another picture showing the same thing. This time we start off with just our products, and the bounce equation got erased here. So let me just quickly write this down. So we see that on this side, I start with just my products. And on this side, I see that I start with just my reactants. But no matter where you start, some of each, or just all products, or just all reactants, when that equilibrium is achieved, the ratio of products to reactants will always stay the same. Here's yet another picture of this. So this one, I'm starting with just reactants. This one, I'm starting with just products. And here I'm starting with a little bit of each. So we end up with different concentrations of my products and reactants when equilibrium is changed. But if you look at the ratio, comparing them, we will find that that will be the same. And that's an important concept that we're going to find later on in the unit. Here's a pictorial view of this. So this is starting with just the reactants, and we see that it will react until I get my equilibrium right here in the middle. And then here we're starting with just the product, but you can see that through collisions it can decompose to form the reactants. Either way, an important concept is that you should have some of each thing in your balanced equation. And so that's represented here. I have my SO2, I have my O2, and then I have my SO3. So I should have at least some of each thing in the chemical equation. So this is very different from some of the reactions that we've been looking at where there's a limiting reactant, where you're going to have a reactant run out. So in chemical equilibrium, because it's going both ways, you're not going to run out. So we've already talked about exothermic and endothermic reactions. So all we are adding is reversible reactions. So looking down here at this exothermic heat diagram, we see that our reactants are a low amount of energy compared to the products. So we know that the heat is going to be exiting. But what if this were a reversible reaction? Well, then I would be going the opposite direction. So this will change the activation energy required. So when I'm going forward, my activation energy is quite little. So you find the activation energy by starting with your reactants and going up to the top of that little energy hill. That little energy hill is called the activation energy. It's the energy required to form the activated complex. The activated complex is where the bonds are broken and remade. If we look at the reverse reaction, we see that the activation energy is so much larger. And that's because our products are our starting point. And so you just draw that little line up to the top of the hill, and we find out that the reverse reaction requires a lot more activation energy. For this reason, if you have an exothermic reaction, when you come to equilibrium, if it's a reversible reaction, you will end up having more products at equilibrium. Let's look at an endothermic reaction. So in an endothermic reaction, we have our reactants are at a low point and our products are at a high energy point. When we look at the activation energy, you start with where the reactants are and draw a line up to the top of the hill. That is the activation energy for your forward reaction. Notice it's a lot larger than the reverse reaction. So if I'm going backwards, my products have more energy, and I only need this little small amount of activation energy to form the reactants. So in an endothermic reaction, because it's easier to go from products to reactants, at equilibrium you end up with more reactants. So the height of the activation energy gives you a clue of whether at equilibrium you'll have more reactants or whether you'll have more products. For an exothermic reaction, you'll end up with more products. For an endothermic reaction, you'll end up with more reactants. In a completion reaction, this is a reaction where one of the reactants will get used up. And then once it's used up, the reaction will stop and it won't go backwards. A good example of this is burning a fire right here. So you take the logs and some kindling and you light it on fire, and it proceeds until all the logs have burned. And you can't go backwards. So you can't take that ash in the fire pit and reverse it and form logs. It just doesn't work that way. So this is a completion reaction. It's not reversible. Down here at the bottom, I have a picture of a reversible reaction. This is a phase change reversible reaction. If I put a little bit of water in a container, water vapor will form, and as long as the container is closed, that water vapor will build up until eventually it will start falling back into the liquid. So I have an equilibrium situation between liquid and gas. And so the rate of liquid forming the gas will be equal to the gas forming the liquid. You also can chemically manipulate reversible reactions. And I know it's a reversible reaction because of that double arrow there. So in this reversible reaction, we can start with a yellow solution, but then I can encourage it by adding a chemical to favor more the product side, and I can turn it orange. And then I can chemically make it favor the yellow side. So I can change it back and forth, yellow to orange and orange to yellow. How is the rate of reaction measured? It is measured through the disappearance of reactants and the appearance of products. So if I take a test tube of hydrochloric acid, so here's all my little hydrogen ions from my acid, and I put in some magnesium. So the magnesium will start to react with the acid. And what you're going to see is you're going to see bubbles form and a gas form. So I can time the rate of reaction by measuring how fast it takes for that magnesium strip to disappear. Or maybe if you're familiar with the pH scale, I can take a measurement of the pH, because the pH will continue to climb as the acid is used up, reacting with the magnesium. I also can measure the rate by looking at the appearance of the product. How fast is that gas appearing and how much do I get? So because this is a balanced equation, the disappearance of reactants and the appearance of products are all related.